Good afternoon, students. So, welcome to our online session of optical communication class. In the previous classes, we have discussed the concepts related to the pin diode, its signal to noise ratio, how we are going to obtain the SNR ratio. That is also we covered in the previous session. Now we are going to learn in details of it how the avalanche photodiode is going to work. The main criteria for finding the avalanche diode is all about its rate, right? So basically what the rate is all about, it's about the ionization rate is an average number of electron hole pair created by the electron per unit distance traveled. Whatever the distance we are going to consider in that particular distance, it's going to be considered by using that analysis as well. So because of that, all kind of things we are going to taken into consideration by using the avalanche photodiodes. Let us see the previous things what we have covered. In the previous classes, we have discussed this graph, all the analysis part and everything. So these all concepts regarding the responsivity also we covered, and we have seen its typical value. Next part, we have seen its avalanche photodiode. Based on its avalanche photo kind of part of it, we have seen its photodiode with respect to the responsivity also we have derived. And the next part, we have seen its SNR ratio. So basically, what is SNR ratio, students? It is a signal to noise ratio. Here, what is we are going to understand in this? We are going to find signal power from the photo current divided by the photodetector noise power plus amplifier noise power, because we do have a two kind of noise. One is for the photodiode detector noise, another is the amplifier noise that we are going to see now. For deducting that one, we are going to use the weakest received signal, and then the photodetectors and the amplifier must be optimized in order to define the desired SNR ratio. The next thing is about the how to achieve the desired SNR part. So to get the desired SNR parts, we need to consider their signal power to the noise power. In the noise power, we do have two types of signals. One signal is about the noise power with the amplifier. Second part is what? Photodetector noise power. This two kind of thing if you consider, then such type of signal is considered to be the signal to noise ratio. Here, to achieve the desired SNR ratio, what are the things we require, students? We have to have photodetectors that must have high quantum efficiency to generate the large signal power. That should be the reason. Second part, photodetectors and the amplifier should also take a noise that should be as low as possible. That should be the next criteria in order to achieve this kind of signal to noise ratio. And always, what is the thing we have to consider? We have to consider that the noise power always needs to be 1. What kind of the things we are going to consider? Here we are seeing that the noise current that is going to pass from the minimum optical power that needs to be taken into consideration whenever we do have a detection end. That means whenever we see the any kind of detectors, when it is taking the value for it, in that particular situation, we have to consider that noise power is minimum. Next thing, the sensitivity. How to get the sensitivity, students? Sensitivity or a minimum detectable optical power, that is a power which is necessary to produce a photocurrent of the same magnitude as the root mean square of the total noise current. What is the total noise current is there, that also needs to be considered. Or SNR ratio needs to be 1. That means whatever the signal power is there and the noise power is there, that must be 1. Next thing, so let us see the part of it in that the photodetectors, what exactly it's going to work. As you can see the model of the photodetectors receiver, we are using an operational amplifier. Basically, what is the use of operational amplifier, students? Here we are using a bias voltage which is in negative direction, right? If we are taking first N type of kind of thing, then we are putting with the positive P type of it. So we are using what? Electron and hole pair of both the end. When we do have this kind of thing, when we do have a photodiode, when we are passing an Einstein energy E is equals to h mu. How we are passing? With the help of load, right? So what exactly we are going to find in that? We are going to see the model of the photodetector receiver. Basically how the receiver is going to work, at what kind of functionality is going to depend. All these things we need to consider in order to find the analysis. So in order to obtain that kind of thing, we are using a model of photodetector receiver. Clear? So here we do have a bias voltage and we do have a photodetectors. Based on that, we are going to find out its output. Clear? Now let us see this part of it. So we have covered what is the things we are going to see in this photodetector receiver equivalent circuit. How do we get that equivalent circuit? Basically, here we are using RC kind of component. One is a resistor, another is a capacitor. We are using series as well as we are using a parallel. So what is the series energy we are passing to the photon? Because photon use an energy, right? How the photon use the energy? It used based upon the photodiodes. What are the photodiodes functionality? Photodiode is used to perform it will take kind of photons and it will convert into electrical pulses. That can be done by the photon. So what energy I am passing? E is equals to h mu. That is the Einstein energy I am passing towards that. So that we are connecting to the whole part of it to the operational amplifier, that is op amp, right? Amplifier, what is the name itself? Amplifier means. So this is what actually the photodiode that has a series resistance RS, as you can see here. And then what is the thing we are using over here? We are using a biased resistor RL, as we have seen in the previous one. This is a RL, that is a biased resistor. We are using the external biasing. Basically, what is a biasing means? We are using an external supply in order to perform the task for that particular operational amplifier. Clear? Then we do have RL and total capacitance is CD. What is the use of capacitor? Basically, students, it is used to store the energy, right, in the form of pulses. So that's the reason we are proceeding with the capacitor. And comprising of the junction and the packing capacitance, that is also there. The amplifier has input resistance as well as they have a capacitance CA and input resistance RA. That we have took. Next part, RS is much smaller than RL. Obviously, the series resistance needs to be very less when compared to the parallel resistance. The reason is that we can able to get the same supply voltage. Whatever we are getting at the initial part, the same needs to be passed to the end. Because of that reason, we are considering this particular part. So basic thing for all the circuitry is what we need to find its equivalent find. How do we get that equivalent circuitry? That is our main intention. Clear? So what is the amplifier is all about, students? Amplifier is a device which increase the weak signal, which increase the strength of the signal. Suppose you're giving 2 volts, it try to make into 4 to 5 volts. Depends upon the types of amplifier what you're using. Whether BJT amplifier, what is a FET amplifier, operation amplifier, all things you already have covered in your previous classes. We are just want to learn the things what exactly we are going to proceed. That is also our main criteria to understand it. Clear? Next thing, how do we get the noise source? Basically, what is the noise source, students? Noise means we obviously get a noise whenever we take any kind of task to our electronic appliances. The one thing which we cannot neglect is the noise, because noise is the factor which always used to get whenever we try to find the analysis of the signal. So that is also one of the things which we need to consider while we are performing the task for our particular signal. So what exactly I'm using? I'm using a modulated signal power P of t that should be there on the detector side. I'm using a primary photocurrent that is given by this formula. Primary current is what? IPH. PH indicates over here it's the primary current. It's a function of time, because always you are using a kind of signal which are varying. That's the reason we are putting a tau t over there. So it is changing with respect to time. Based on that, we are going to find out its analysis. So based on that, we have put IPH of t is equals to eta. What is eta is actually, students? It's the efficiency. Q by E. Q by E is actually what? E is nothing but the h mu, right? We know the Einstein energy. And that is what P of t. P of t is what actually? The modulated signal power. So we got the current based upon the power. What is the I is equals to P by E? You know formula, right? Power is equals to energy into time. If you want to find the same phenomena, I want to get that I value from that. I can find I of t is equals to eta q by h mu of P of t. I can able to find out by considering these kind of parameters. That is nothing but the noise current we are obtaining based upon that phenomena. So let us go ahead with that same part. How we are going to get it? So first thing what we said that the primary current contain average photocurrent that due to the DC signal, because what we are signal we are passing, we are giving DC supply as well, right? To the what kind of part? To the signal part. So IP and the signal current IP of t, how it's vary? One I am saying as DC signal. DC means obviously it should be either 0 or 1, because 0 indicates ground, 1 indicates supply. So I am considering whatever the external biasing supply I do have, I am giving in terms of DC supply. So based on that DC supplies, I can able to find out its analysis as well. That's how we are going to obtain its analysis and we are going to find its current. Now move ahead with the next part for a pin photodiode. What is a pin photodiode? How to get that? So we can say mean square signal curve current IS square is equals to IP square of t. That we put it for avalanche photocurrent. What is the current? We are just adding with multiplication factor as m. So the same for R pin photodetector diode, the square mean value, how we got that? By using the IS square is equals to IP square of t into m square, because we are doing the current square, you know. So that's the reason we have to use the current value. Based on that, we can able to obtain and we can able to find out. Clear? This is the way we can able to find the current analysis for our noise source, because in our systems, whatever the electronic systems we do have, in all the kind of systems, the one thing which we need to consider is all about the noise, because the noise is the one which can fluctuate, which are the factor which we are degrading the signal strength. In order to get the signal in a desired form, we must consider its noise source. That's what we are considering its noise source. We are able to obtain its current as well. Next thing, how do we get the sinusoidal varying signal? Because we are saying previously for DC, right? DC means it's not varying. It's either has 0 or it has 1. What about the varying signal? That is a continuous signal or analog signal that's always try to vary with respect to time. So whenever we do have any kind of signal which we are varying with respect to time, such type of signal is considered to be the sinusoidal signal. So for sinusoidal and varying input signal of modulation index m, if you do have this kind of thing, you already have seen the modulation of analog signal, right? So if you had analog modulation index of m, if you want to find the signal value, only the thing what we need to consider is the modulation factor. So how we get the current? So IP square here, as you can see here, right? IP square of t is equals to m square by 2 IP square. So this is what IP square is, nothing but the signal component of current. That's how we can able to obtain its noise source as well. Clear? So this is the way we obtain it, and we can able to find out its noise source. Next part, what we need to see is about its functionality. How the short noise of quantum noise, how we are going to get that? So in order to achieve this kind of thing, it's going to arise based upon the statistical nature of production. Means how the current is going to generate it. Based on that, we are going to find its short noise. Now let us see the short noise or a quantum noise, student. So how do we arise that one? In order to get that, we are using the arises due to the statistical nature of production and the collection of the photo carriers after photons are incident on the photodetectors. The main thing is regarding the Poisson distribution. Let us proceed with the Poisson distribution. Basically, what is the Poisson solution? The Poisson ratio is the one whose analysis part is that it needs to perform a task based upon the ratios. Basic thing, what is the ratio of it? In all the ratios, we need to obtain the analysis part of it. The main thing is about the analysis, and then analysis ratios we have to obtain. Based on that, we need to find its functions. So Poisson ratio, how do we obtain? We have seen in our maths also. In engineering maths, we do have seen that whenever we do have any Poisson ratio, ratio is what, nothing but e power minus lambda power r by r factorial. That is what actually, that is for the Poisson distribution, And one more thing we have seen is Poisson ratio depends upon the lambda. Basically, lambda is nothing but mean and variance. What is the use of finding the mean and variance? It is used for statistical analysis. That means whatever the statistics we do have, if you want to find the analysis obtained for it, we can able to find out its Poisson distribution. That's the reason here it's mentioned that we can able to find short noise or quantum noise by considering its Poisson distribution and Poisson analysis. So based on that, we can able to obtain its functionality. So we are proceeding with the same factor, and we are seeing that whatever the fundamental property of photon is there, it is going to for taking the detection, correction, generation. These are the three things which we need to consider in any kind of electronic world. One thing is about detecting in the sense, if you had any kind of wire, if you want to see whether wire is suitable for what kind of load, how do we get that? We are going to go for testing first, right? What is the testing means? We try to connect with the refrigerator, we try to connect with our different appliances like a heater, we try to connect with the other kind of appliances. We try to see how much resistivity, means the capacity of the wire is there, how much it can sustain the load, right? The same phenomena, we are going to see its detection as well, because the photo detection is the fundamental property to find short noise. Similarly, the next part is regarding the sets. How do we optimize the sets? Sets are lower limits on receiver is going to perform the sensitivity when all the conditions are optimized. Whenever we do have any kind of condition, when I want to find out how much it's optimized, the main thing is regarding the optimization. Based on that, we can able to find out its analysis. We are going to achieve it, and we are going to receive that analysis based on that. So based on that periodicity, we can say that the quantum noise current has a mean square value in the bandwidth. Whatever the value we are considering, that is proportional to the average value of photocurrent IP. Mean square quantum or short noise current for a pin diode detectors or photodiodes, that can be going to obtain it by considering its IQ square is greater than or equals to 2q IPV. That should be the next criteria. The mean square quantum or short noise current for avalanche photodiode is given by IQ square is equals to 2q IP bandwidth, B square, whatever the factor m we do have into FM. What is FM is all about? It's nothing but a noise figure. We are going to find figures also, right? Bandwidth as well as the figure of noise we are going to see in order to find the nature of avalanche process, and we are going to use a multiplication factor of m for avalanche photodiode. That's the things we are going to see. That's about the analysis part. Next thing is regarding the functions. How do we got the functions also? Based on the functions, how we are going to obtain? We are going to analyze that functions. Based on that, we are going to see its properties. So till now, what we discussed, students, we have discussed about short noise or quantum noise that is going to be there with our property. That is also we are going to cover. Next is photodiode dark current. What is the photodiode dark current is all about, students? It is a current that is a continuous form that is going to flow without any incident light. Means what? We are not passing any light, but still our current is going to flow. How is what is the thing? How it is going to obtain it? That is also thing we have to understand. That's what here we had a concept that related to the bulk dark current. That is due to the thermally generated electrons and holes. Based on that, we are going to obtain a specific current and a specific value. We are going to obtain it. In that situation, we are going to obtain the current that is nothing but the bulk dark current. So how do we get that dark current? That is given by I of dB square is equals to 2q ID of B. What is ID, student? Is nothing but the dark current. B is nothing but the kind of bandwidth or the magnetic field part we are going to consider, and q is the number of charges which we are going to obtain for our current which we are passing with the help of photodiode. Clear? So next thing, for the avalanche part of it, the diodes, whatever diodes we are considering, that should be dark current IDB of square is equals to 2q IDB BM square of FM. What is FM all about? It's a figure of merit. And the next part for ID, how do we get the ID is all about? It's the primary detectors that is used for the bulk direct current that is proportional to the active area, because we do have such currents which are in active elements that we're going to generate in terms of pulses. Based on that, we are going to generate its functionality. All the functionality we are going to obtain, and we are going to find its current. So based on that, we can say that the proportional to the active area. Next thing, how do we get the photodiode dark current? In that, first thing we need to know the surface dark current as well. We are just using that. That's how we can able to find out its photodiode dark current, students, and we can able to simplify the answers for it, and we did as well. Next part is regarding the thermal noise. How do we obtain the thermal noise? Assuming that the impedance of input of amplifier must be greater than the load resistance ZL. That is the one thing we need to keep in our mind when we talk about the thermal noise. Next thing, photodetectors. What is the use of photodetectors? It is going to contribute major in thermal noise. That is IT of square is equals to 4 kBT of RL by B into B. So what is this KB actually, students? It's a Boltzmann constant. What is C actually? It's absolute temperature that we need to see. R is the load resistance. B is the kind of magnetic impedance. If it's have some sort of thing that we are going to use by the term B, right? So this is the things we have to consider for thermal noise for our part. Next thing, how do we obtain the total photodetector noise current? So how many types of things we need to see? First thing, dark current, then the signal current, that should be uncorrelated, that should be a separate one is there. There is no correlation between the two things. Next thing, total mean square noise current, that is also going to be taken into consideration whenever we talk about these kind of currents. So IN square, that is nothing but noise current square mean value. If I want to find for that, then I can use it by taking the Q. Q is what? How do we obtain the Q? It's dB is nothing but what we have seen the previous one, no, right? Dark current, and ID of this is nothing but the current due to the load we had. Then the threshold current, we do have all the currents we have seen in the previous one. We starting from the starting, all the types of currents. What else we have seen? So we have short noise also, noise current also we have, starting from the noise source and the photodetectors, all the things we do have. And then considering these all parameters into consideration, we can able to find out its total current of that noise. That's what we had. The pin surface dark current is IDS for surface. Clear? What is the previous one? This is what current due to what? It's a bulk dark current IDB. This is for bulking part. Clear? So previous also we do have this one. IDB square also we have find it. That is nothing but square mean value of it. If you use all the currents into the consideration, including the thermal noise current, we can able to find out the what total current. The bulk current we have taken, the surface dark current and threshold current, all the kind of currents if you see into consideration, even the point of Q, if you see that, then we can substitute this all things by using the figure of merit of B plus this is what 2Q IL of B. This is nothing but threshold current we have just now seen, K into KB, threshold voltage of that into T by RL of B. If all the points into consideration, if you want to find out, we can able to find it total photodetector noise current. Clear? So we can able to obtain that, and we obtain that as well. Next criteria is that, students, how to find the signal to noise ratio. That is very very important derivation for us to find out. First, signal, what is the signal power? IP square of m, because m is a multiplying factor, you know. And noise current, what we have just now found, this is the previous one, this is the noise current, right? 2q IP plus ID m square f of m of b plus 2q IL of b plus 4 kb of t by RL into b. This all thing is nothing but the total current due to the noise. So this also we obtained, we substituted that thing, we can able to find out signal power to the noise power. Signal power is what? IP square of m square, factor is there. Then the second one, noise power, we have taken. So here they said a point. For pin diode, the dominant noise current is a thermal noise, and for avalanche photodiode, the dominant noise current is due to the photodetectors. Because for avalanche photodiodes, we are considering, based on that, we can able to find out its current, and the signal current and the bulk dark current are multiplied by the factor m square. Depending upon the surface dark current, it's independent of m square, and after taking this point into consideration, whatever f of m, whatever the f of m is also going to increase with the value of m. If we substitute these all parameter into our equation, so wherever m square is there, all we are replacing with the factor of m power of x. So there must be a optimal value for m which give the maximum signal to noise ratio. If you want to find maximum signal to noise ratio, so that if you want to find out by using the modulation index, if it is equals to m, and for figure of merit is approximately equals to m power of x. If I use to find the next value of figure of merit for optimal value for it, I can use this relation. 2q IP plus IL is there, no, that we are replacing with the factor 2q IL plus 4 kb of t by RL divided by xq IP plus ID. Somewhat it's not visible over here, that's what ID. So this is a complete signal to noise ratio. Optimal power for this factor for the modulation index m of x plus 2, that could be written as 2q IL of 4 kBt of RL by xq IP, that is nothing but the peak current we do have. Then this is not nothing but the dark current, correct? Both the things we took it and we can able to find out the signal to noise ratio. Clear? Next thing is regarding the functionality. How do we get the response time for our detector? That is the next concept we are going to see. Basically, what is detector response time, students? So we are having a type of PN junction. Here we are using a load to that. Here is our reverse bias voltage we are connecting to the P type of material. We do have optical power at the one end. I want to find out width of this. So whenever we do have a diffusion current which allowing the P material to get passed towards it, and diffusion region start getting the wider and wider until and unless you should have the carrier drift, and the holes are try to make this into the compact one. So this is the nothing but a detector we do have, and we are going to find its response time towards that. We can able to find its analysis based on the detector part. So based on that analysis part, whenever we want to find the response of it, we can able to use it and we can able to find out detector part. So here we do have a detector response time. Based on the response time, we can able to find its functions. So basically, what are the functions we are going to see? First function is regarding how the response time is going to increase based on the factor. What are the response time we are going to see, and how the response time is going to differ. What are the things our response times are going to make into the clarity for that. That should be the analysis part we need to see. Based on that, we can able to find its response. So here let's see the function of it. So detector response time can be obtained by taking the major photon that is going to absorb the current towards it, the photon carrier current in the depletion layer, whatever the depletion layer we do have, based on the phenomena, whatever the values we want to find out, by taking the drift. How do we get the drift depletion region, students? By taking the drift current density. The current density given by the factor J of the drift, we can take it, and some photons is going to absorb and some photons going to take outside the depletion layer in the bulk of the semiconductors. Based on that total depletion, if you want to find out the current towards that, we can able to obtain by using the drift. So first drift is regarding by taking the J total. How do we get J total? The J total can be obtained by using the phenomena of the drift current, that is given by drift current dr plus current density of diffusion dj of diff. These two are the two factors, right? Based on that, we are having two factors. Based on this, it's going to be used for that particular analysis. Okay, so by using the analysis, we can able to find out its drift current and drift analysis of that, and we can able to obtain J total, that is equals to J of drift plus J drift of differential. That is J differential is nothing but diffusion current of density. that is given by J drift. Clear? So by using these two conditions, by using steady state condition for total current density, by using this phenomena, J total is equals to J drift plus J drift of it. So how do we get that drift value? By using this formula. Value students, how do we get density students? Density is nothing but the current by area. So that's the same phenomena I'm using. Current is IP by area is A is equals to Q phi naught into 1 minus e power alpha s of width that I'm using, where A is nothing but photodiode area and phi naught is nothing but the incident photo flux area, right? Flux, what is that? Flux per unit area. That is nothing but the phi, flux. This two I am taking, and what is the phi actually? P naught into 1 minus RF by AH mu. That is not visible. Note it down this for that phi, whatever the phi naught we are taking, phi naught is equals to P naught into 1 minus RF by AH mu. Clear? This is the formula for finding the flux. By substituting these two kind of things, we can able to find out the density. What kind of density is all about? It's a drift one. So what is the drift one? It says that whenever we have major photons that is going to absorb, the photo carrier create in depletion layer, that is also going to be taken care. They drift across the depletion region, that's giving drift current density to JDR. Then some photons that going to absorb and some photons create outside the depletion layer in the bulk semiconductor that diffuses into the depletion, giving diffusion current density JDIFF. That is nothing but the diffusion current density. And what kind of condition we are considering for this? Under steady state condition, the total current density is given by this particular formula, right? So by using these all kind of parameters, we can able to find out its drift current. Clear? So this is the way we can substitute and we can able to obtain its detector response time. So total detector response time by using this formula, J diffusion density current given by Q phi naught alpha s of LP my 1 plus alpha s of LP e power minus alpha s omega. We are multiplying with the factor. We do have this factor. So this factor we are multiplying with the first one, Q phi naught, minus the second factor we are multiplying. What is phi naught value? This is there. We substitute this whole in the main formula for drift as well as for our total. If you use these two things, we can find the answer of total density of our current. Clear? So that's by using LP. What is LP? Diffusion length. NP N naught is nothing but the equilibrium hole density, and DP is nothing but diffusion coefficient for the hole. By using these all kind of parameters, we can able to obtain its analysis as well. Able to find out J total of this by using Q phi naught into 1 minus e power alpha s of omega by 1 plus alpha of LP plus Q P N naught dP by LP. What is dP is all about? Diffusion coefficient for hole, and LP is nothing but diffusion length. Chalo, back piece rakh lo pura. Substitute the conditions for that, and we can able to analyze the functions. So this is the way we have done it, and we can able to find out its total. So what is the total, students? So D diffusion plus D of drift. J of drift. Drift already we had, no? This is a drift one. Q phi naught into 1 minus e power alpha s of omega, and the second one what we do have is drift value for it. So we can substitute these parameters. We can able to analyze that one at that particular analysis part. We have substituted and we can able to analyze these functions by using the drift current, by using the analysis for diffusion density as well as the drift density. If you use both the things, we can able to find out its time as well. So first of all, we are taking the density functions, then we can realizing these functions by using the density. Clear? Next part we need to understand is response times. That is an important, very important part. That is how do we get that. First thing we should know diffusion time. Next we should know the transient time, and we can find its time constant as well. So that's the analysis part we are going to see, and we are going to analyze that one as well. So that part we are going to see in the next class, students. So this is about today's sessions, and we are able to simplify all the answers, and let us move ahead with the next topic which we are going to see in the next class. So take care of yourself. Have a great day. Be safe. Goodbye.